Okay, so what are vectors? All right, I guess that it's just as easy to talk about things that aren't vectors. So obviously in physics and chem, things like that, as I said there, in some experiments, things are just measured by their size, distance, speed, mass of an object. Okay, other things are also measured by their size and their direction. Okay, so displacement, 10 kilometers northeast, velocity, positive, indicating direction. So 10 meters per second in a positive direction, or negative 10 means a negative direction. So those sort of quantities that indicate size and direction are known as vector quantities. Okay, so how do we represent them? All right, so mathematically, vectors, okay, measured by magnitude and direction, and so they're just measured in maths by an arrow pointing in a particular direction. Right, length of the arrow gives the magnitude, the direction of the arrow gives the direction. Right, now despite in a Cartesian axis, they're all straight lines, all with same gradients but different y-intercepts. They would be different lines. In vectors, each of those line segments represent identical vectors because they're the same size and they're the same direction. All right. We can also represent our vectors as column vectors. So the column vector AB, the arrow on the top saying from A to B, as 3, 2 represents it's 3 to the right and 2 up. All right. In terms of notation, okay, math books and things like that often represent vectors as a bolded letter. Very hard for us to write in bold, so instead we use a tilde, which is a little squiggle line underneath, or the vector from A to B, right, where the arrow represents a direction, as it says there. All right, so the magnitude of a vector, or the size of a vector, a bit like our complex numbers, it's the modulus, the magnitude. Okay, and I guess if we've got a vector that's a particular size and direction, well then the size of this vector is x across, x up, or y up. And so we have good old Pythagoras. There's my magnitude. All right. As I mentioned a bit earlier, all these vectors are equal. So they don't need to have the same starting point. All right, so in reality, as long as the vectors are parallel and of the same size, they're equal. A negative vector simply means it's in the opposite direction. All right. So if we're going to add vectors, okay, so the vector u plus the vector v, we do what we call top to tail. So the top of one vector onto the tail of the other. So I go from A to B up to C. Vector u plus vector v, and the u plus v is the resultant one. All right. Column vectors, we can only add vectors that are column vectors that are equal. So u plus v, 4, 1 plus negative 1, 3 is 3 fourths. Sort of makes sense, doesn't it? Scalar multiplication, so this is where we start talking about vectors and scalars. Scalar meaning it's just a magnitude. So a scalar is a constant. So if you increase a vector by a constant, it's just that times bigger or that times smaller. All right. If the constant is 0, then 0 times any vector would be 0. So if you have a look at these two examples, they're nice ones. All right. There's vector u. Well, 2u is just the same direction but twice as big. A half u, a half the direction. Negative 2u, twice as big, but in the opposite direction. All right. Zero vector is denoted by 0 and represents a line segment of 0 length that has no direction, no magnitude, etc. All right. So if we come on to subtraction, if we want to subtract vectors, we actually add the negative. So here's my vector u there. Now, if I want to add v, I would go that way. But if I want to subtract v, I come back the opposite direction, which is what I've done over here. Minus v, and so there's u minus v there. All right. Now, a bit of, I guess, vector manipulation. Two vectors a, b, and b, c, we have from vector a to b to vector b to c, the resultant vector is ac. So it's almost like those b's cancel a little bit. And here, if I start from A to B to C to D to E to F and back to A, it means that we're back to our starting point. So we're back to 0. All right, so that's the true of any polygon, any shape. From A to B to C to D back to A means we're back to where we started. Parallel vectors, same direction or opposite direction, okay, either one. So they are parallel if one vector is a product of the other, whether that product is a fraction or a rational, irrational, positive, negative, it doesn't really matter. So clearly in here, if I multiply the vector u here by -3, -3 by -2 is 6, -3 by 3 is -9. So they're parallel because u is equal to -3v. Often we use a vector u as a reference point. Okay, so if I even come up here where I've got this A, B, C, D, I might have the vector O here. So from O to A, OB, OC, OD. Yeah? And so from the vector AB, well, it might be the equivalent of traveling from A to O and then going from O to B, which is negative OA plus OB, which is the same as AB minus OA. Yeah, so we often reference the vectors from a fixed origin point. There we go, so the vector OA. So vector A can be represented by the directed line segment, A1, A2. Vectors in 3 dimensions just means we have 3 columns, right? And our 3-dimensional vectors, we have our X and Y plane, which is what we typically work with. And our Z plane is the elevation, if you like. So there's my XYZ plane, all right? And in vector notation, I might use A1, A2, A3. So let's just have a look at a basic example. So the vector A is equal to from O to A. Where's O to A? So that's O to A there, yeah? Now, so it's that sort of length of the rectangle. So all of these vectors here that I'm about to mark in green, they are all, okay, they are all vector length A because they're the same size and they're the same direction. Vector G is from O to G, upwards. They're all vector G. I'll go with the lucky red. OC is this way. Probably should have put arrows on my green. Okay, so they're all vector C because they're the same size and same direction because we've got a parallelogram there or a cuboid. So let's find the definition for OB. Where is OB? I shouldn't have put those bloody thingos on them. Let's just uncover some. Let's uncover all of our letters. There's B, there's A, D, G, there's O, there's F, there's C. It's a bit easier. All right, so what do we say? We have to find OB. OB is this diagonal here, isn't it? So how do we get from O to B? Well, there's a couple of ways. I can go from O to C plus C to B. And O to C is the same as going from O to G. Well, sorry, my bad. O to C is O, in fact, O to C. So it's C, which is C. CB is the same direction as OA. I'll try color code. So we get C plus A. What about OF? O to F, where I can get from O to F, it's along there. So from O to F, I could go OG plus GF. And where's OG? OG is the blue line up, which is just G. And then GF is the same as OC, which is G plus C. What about GD? It's just that parallel line, which is the same direction as OA, isn't it? So that's just equal to A. And I should really be putting little tildes underneath all of my vectors here. What about GB? GB is top diagonal, bottom right. Yeah, so I could go, and it doesn't matter which way we pick, I could go from G to D plus D to E plus E to B, which is equal to GD is equal to the green line A, DE is equal to the red line C, and EB is the opposite direction to the blue line, so it's minus G. Finally, FA. Where's FA? It's the opposite corners. So FA could be, I might work FE plus, what if we go EB plus BA? What does that give me? It gives me FE, which is A. Now I go from E to B, which is the opposite direction of OG, so it's going to be minus C. And then I go from B to A, which is the opposite to OC, so it's going to be minus G. Oh, sorry, boys. I should have, EB is minus G, isn't it? Got my order out around the wrong way. Minus G, not that it matters, but I want to keep it true to the order that we've done here. All right. So that's how we work around our objects using some vector notation. All right. Now, what have we got here? We've got a little bit of a definition for us. Linear dependence and independence, all right? So what makes something dependent? So a set of vectors is said to be linearly dependent if at least one of its members can be expressed as a linear combination of the other vectors. All right? So it's linearly independent if it's not true. So in other words, can I write one vector as a product of the others? All right. So where's a good example? Well, let's come straight down to example. Oh, I'll get to it. So for example, for two vectors are linearly dependent if and only if there exists a real number that MA plus NB is equal to 0. In other words, if I rearrange, A is equal to negative N on MB. So in other words, I can write that vector in terms of that one, providing we don't use 0. For a set of two vectors, non-zero vectors, they're obviously, if I extend this further, A is equal to sum KB, which means one's a factor of the other, which makes them parallel. All right. Now, for three vectors, same sort of thing applies. And what we aim to do is we try to write one vector, okay, in terms of factors of the other. So we come up with some simultaneous equations in reality. So let's have a look at these vectors here. What I want to try to do to prove dependence, I need to be able to write u is equal to some mv plus nw, where m and n is just a constant. Now I could have put v is equal to mu plus nw. Any combination works, all right? And what we're going to do is, so I'm going to say u has to equal some m times v, which is 213, plus n times w, negative 101. So if I do that, u is 3, the first element, 3, equals m times the first element, which is 2m, plus n times the second element, which happens to be minus 1. So we'll go minus n. So if you like, there's my 3, 2m minus n. All right. Second element, 4 is equal to mv, which is m, plus n times 0, which is 0. So that's those elements. And finally, I'm going to say that u, which is negative 1, is equal to 3m plus n. All right. Now, if these will be linearly dependent, if there's a value, if there's an m and n that satisfies these equations. So from here, I know m is equal to 4. So if I substitute m equal to 4, say in there, I'll get 3 is equal to 2 times 4 minus n. Therefore, n is equal to 5, if I've done that right. Yeah. Now, if I substitute both of these into this equation, the third equation, negative 1 is equal to 3 times m, which is 4, plus n, which is 5, which is false. Yeah. So that means I can't write one as a combination of the other two. Therefore, linearly independent. All right, maybe just have a read through and a listen through that again. It's all brand new, but yeah, and then now have a go at some of those 28 questions.